In this exercise, we're going to discuss how to use optimizers to fit an FOPDT to processed data. We'll manipulate the process gain, process time constant, and process dead time, and then use a minimizer to perfect that so that the error between our process data and our FOPDT model is minimized. Here we have one way we can numerically do this with a with an explicit solution per time step to our FOPDT equation. And an alternative is to use a graphical fit to create a guess and then use Matlab functions such as the optimization task or fminsearch to further optimize our fit. So let's briefly discuss how we'll do this with optimizers. The first thing we'll need a function to be used with ODE45 that will give us the derivative at any time for our FOPDT equation. The second function we'll need is a function to take arguments such as the gain, process time, and dead time, and simulate that FOPDT equation for the length of the trial given the input data from the process. Finally, we need an objective function that will use the least squared error or another error metric and compare our process data and our FOPDT model. Ideally, this objective function would return 0 if our FOPDT were perfect. And our optimizer will then use our objective function in order to measure how good our FOPDT fit is. So let's first look at how we'll simulate some data. We're going to generate some simulated data just using the simProcessData function. We'll first create a number of steps as well as a time points and our input vector, where we'll use some steps up to 1, down to 0.1, and then to 0.5. We'll then create the simProcessData and then graph that. Our simProcessData function right here takes a process, and for this dydt, this process function, returns the derivative of a process, and then our simProcessData will create process data for us by stepping through all of those input points and integrating it with ODE45. As we run this section, we can see that we create output data for our process given the input data down on the bottom. We'll then try to create an FOPDT that mirrors this. The first way we can do this is using fminsearch. fminsearch is a native to Matlab and also doesn't use derivatives similar to some other solvers. In order to use fminsearch, we need to provide it with a guess and then our objective function. So we can see with our guess, we just create a column array with our 3 variables, our gain, our process time, and our dead time. Let's look at how we create that objective function. So if we scroll down, here are the 2 functions we use for creating the process data. One for creating the FOPDT and the other one to integrate it given the inputs. We have something similar. We first have this function called FOPDT, which gives us our derivative at any given time given our inputs, and then also given our FOPDT constants, our gain, our time constant, and our dead time. We have this block in the middle with the try-catch that simulates our dead time by delaying the input using interpolation. And then we have our dydt, which gives us our derivative. The function simModel then takes our FOPDT constants, as well as the time array, input array, and the output array in order to simulate the FOPDT model given the inputs over the course of the simulation. Finally, our objective function down at the bottom will accept different FOPDT constants into the simModel function and then take the sum squared of error between the resulting model data and the process data created before in order to return the objective value. Using the sum squared of error, the closer the model gets, the lower the objective function will be. Back up top with our fminsearch function, we parameterize this function using the @ symbol, similar to what we do with ODE45. We pass just the function that we care about, which is x, or the FOPDT constants, and then we pass our objective name, our function name, objective, and its arguments, which are x, t for time, u for the input, and yp for the process output data. The results of fminsearch, the optimized parameters, are stored in solution. Then we use ym1 and ym2 to simulate both our initial guess and our final result after the minimizer with fminsearch. Then we use our figures to plot and verify our data. Let's go ahead and do that, and let's look at our results. So here's our results for fminsearch. You can see that the three values we got were 3.0,148 for our gain, 1.8 for our process time, and 3.7 for our dead time. You can see our initial guess in solid blue did not do a good job at matching the process data with the black X's. But our optimized fit with the red dashes does a decent job at mirroring the process data. Graphic results are a great way at looking at how well our model reflects our results, or our inputs, I should say. Another option is to use the optimization task within Matlab. To do so, we'll use this task toolbar and we'll select optimize right here. If you need more functions, such as what we'll use here with the least squares nonlinear solver or other solvers, you can download the optimization toolbox. We need to first create a parametrized function handle. I've done this by naming this objective parametrized to keep everything clear. This is a function handle that will only take the argument x for our FOPDT constants, but calls the objective function as shown right here with x as well as our time, input, and output arrays. We'll also create an array xmax and xmin to store the minimum and maximums for our FOPDT constants. You can see our results are shown as solution, which is the FOPDT constants, and objective value. Hopefully this goes to 0. This started running before. We'll go ahead and run it again since I stopped it and it didn't reach a conclusion. We've chosen a least squares model and with lower and upper bounds. Our solver is the least squared solver, and our function handle is what our objective function will be selected by. And you can see I've already selected our function handle objective parameterized. If we had a function that already worked, we could select from the existing functions that exist within the workbook. However, we have a function handle since we need our function to be parameterized. We have our initial point, which we've already included below, and then we have lower and upper bounds from our workplace. Generally, we need this section to be run first so that we're able to access these. And we'll go ahead, we'll display our solution, and then we'll graph it similar to what we've done before and look at those results. You can see our output. I'll go ahead and make that bigger. Our output shows the number for our three variables in the top left, our evaluations, and you can see the residuals, or our residual error, decreasing with each iteration. We'll go until we hit the limit of error that we've predefined. And we'll see our graph be created. Let's go ahead now. It reached a local minimum. And so let's look at our output. Our output's pretty similarly. We have a 3, a 1.8, and a 3.7 for our FOPDT constants. And we can see that the red dashed line again reflects pretty well what's going on. So you have two ways to use optimizers to fit FOPDTs. I'll briefly just review what our three functions are, since that's where I see most people having problems. The first two functions were done to simulate the model and get us our process data that we're fitting other models to. Then we have three functions. One that returns the derivative of the FOPDT, shown here. One that integrates that using ODE 45, the FOPDT constants, and our input data from our process. And the final one that will compare the two, with the first argument being the arguments we want to manipulate, so our FOPDT arguments. We'll then use that in either fminsearch or an optimization task in order to optimize and fit to our data. Let me know if you have any questions below, and we'll move on to some practice with this now.